I'm gonna start. I mean, is it something class related or is it? Okay, so let's go ahead and get started. So first of all, I did put the activity that you did last class. What I did is I looked closely at the what was it, the and instruction. That one I looked like at everything, and I was very picky on purpose. Because some of you might have noticed, like I just took off like 1% because you didn't have a red line in a certain area, and you might go, why did you? Well, I did that on purpose to emphasize that when you do these diagrams, because eventually you have to do a diagram for every real instruction in order to do the control unit that we're going to do in a couple of weeks. But before you code that control unit and you have those diagrams, you have to be very meticulous. You have to really look and see, what do these signals have to be? What is the path the data is taking? Because if you have the wrong diagram, right, if something's missing, that instruction is not going to work. Okay? And there's 30 some odd of them. I mean, that's one of the reasons why I'm going to allow for the, the final project where you got to get the auto working. How I said I'd allow up to 4 people in a group. That's the reason, because if you have 3 or 4 people, you should be able to help each other and double check. I was once in the Air Force in a previous life, and in the Air Force, in the job I had, because what we were doing was so critical, we had to have 3 people look at our work before we would actually, it was software that got uploaded to a satellite. But it was so important that you couldn't trust just one person, because it's very easy for one person to miss something, no matter how good they are. So we had 3 very good people look over the work, the software, before it was uploaded to the satellite. And so you got to kind of look at that way. You got to all help each other and check each other's work. Okay, so I really looked closely at the and instruction, and the solution to it is the same as what the sub instruction was that we did in class, and it's also on Canvas. The only difference is the AW font is a different code. That's the only difference. Okay, and you'll see when you start to do the diagrams for the various instructions, you'll see that there'll be a group of instructions where the data path is all the same and all the control signals are the same, except for the ALU font. That will be the only thing that's different. Okay, but you're not going to find out what those group of instructions are unless you actually sit down and start doing the diagrams for each of the instructions. Now, the other instruction, I just looked to see if something was there, and I checked it. I didn't look closely at all. So I would recommend that if you did miss things on this instruction here at the end, I would recommend that you go over that 4i and just make sure you didn't miss anything on that. And again, the solution for the 4i is the same as the add I. Okay, the add immediate that was in class again. The only thing that was different was the ALU funds. Okay. There will probably be another activity where you have to also trace out the data path and the control signal. Not today, but probably in a few weeks. Okay, also I listed up here, what's left in the quarter. Now this is all on Canvas, but I thought I would just put it here in class and talk about it a little bit, along with what's left that's due. But I'll go over, what's left in the schedule, and also what's left that's due after we go over what we need to go over for the lecture today. Now today's lecture, very similar format to the past, the one on Tuesday of this week. But remember, in that class, at the end, you had enough information to do 2 more modules in the order, right? The ALU and also the immediate generator. And we went through some data paths and control signals for some various instructions. Well, today it's a similar type of deal. Is that at the end of the class, you'll have enough information to do 2 more modules. Okay, both the branch control generator and also the branch address generator. And we're going to go through for another 5 instructions and look at the data path and the control signals for those instructions. Now, I don't think it's gonna take as long as what it did on Tuesday because you've already had some experience, doing these data packet control signals. So I'm hoping you got a little bit of experience now, so maybe I don't have to go as I won't say slow, but as methodical as I did on Tuesday. I can maybe take a few shortcuts. Okay. But if I'm going too fast, please slow me down. Okay. All right. Well, before we get to the actual diagrams here, there's some information that we have talked about previous to today that does apply to what we're going to discuss now. And that's, remember, you had a software assignment where you had to do some conditional statements, right? Branch instructions in assembly. And remember, we talked at that time that even though there's a whole bunch of branch instructions, there's over a dozen, there's probably like, I don't know, 15 or 16, something like that. Most of the branch instructions are pseudo instructions. Okay, so they're made out of real instructions, or they might be a single real instruction, but they have like a special value. So there's only 6 real branch instructions. And again, the Otter, the processor, only needs to be able to execute those real instructions. In addition to there only being 6 real branch instructions, they're in mutual pairs, okay, mutually exclusive pairs. Okay, branch less than and branch greater than or equal to go together, right? Because one is false, the other is true, and vice versa. And then there's branch if less than unsigned, branch and greater than or equal to unsigned. So the only difference between these 2 pairs is one is treating whatever the comparison is, the data as signed, and the other one's treating the data being compared as unsigned. Okay, and then you have branch if equal and branch if not equal, and of course they go together, right? If one's true, the other's false. Okay. So you see what this means, because there's only 6 real branch instructions and because there's 3 pairs of them, right? You're going to see that only 3 comparisons are needed. That in this module, this branch condition generator, you only have 3 conditions. And you're going to see, and we'll talk about it more a little later, that in Verilog, system Verilog, you're just going to need 3 if-else statements. Okay, that's all this module is going to be, is 3 if-else statements. An if-else for each comparison. Now, also, last class, because you started working on hardware 4 that had the, as part of it, the immediate generator, right? The piece of hardware that generates those immediate values. Well, branch instructions have B-type immediate values. And if you look at any of the branch instructions in the instruction manual, you'll see B-type immediates. Now, we're also going to talk about jump instructions too, and see the data path and control signals for jump instructions. And a jump instruction is just an unconditional branch. And there's these 2 here that are real instructions, JAL. We'll talk more about that, what that means coming up, and also JALR. But right now, just know that the JAL instruction, the immediate for that instruction is a J type, and then the JALR uses an I type immediate. And as we talked about, right, immediates are just numbers. Here with either the branches or the jumps, that immediate value, right, that integer, it's going to be a signed integer, right? And if you think about it, it makes sense, because when you're jumping or branching in a program, you may want to go ahead in the program, or you may want to go back in the program, right? And remember, each instruction has an address, and the first instruction always starts at 0, right? So if you're somewhere in the middle of your program and you want to go back to a previous instruction, well, you need a negative integer. Okay? If you want to go advanced in your program, you're going to need a positive integer. Because what you're going to see is the way the hardware gets the jump or the branch to happen is it provides an offset to the program counter, right? Because what is the program counter providing us again at the output? What's here at this output? What is it? The instruction here? Address of the, yeah, it's an important difference. Remember, the instruction's out at the output of the memory monitor. But here at the output of the program counter, that's the address of the instruction that's going to be executed. So if you offset this address, you're offsetting where you are in the program. You're offsetting at what instruction you're at. Okay, so that's what these branch instructions and jump instructions do. They offset that program counter output, which is providing the address of the instruction that's going to be executed. And then, as we talked about before, remember in RARs, right, it requires a label instead of an actual number. But you'll see as we go through the hardware, right, and show the data path and the control signals, we're using numbers. Okay. All right. So, one other thing I want to mention, and I sent an email about this because it was something I forgot to say last class, and that was with the ALU, unlike previous assignments where you have to come up with the test cases, for the ALU, we provide the test cases for you. Those test cases are on Canvas under meeting 7, right? The meeting where we talked about the ALU and the immediate generator. And if you go to the very end of my notes, there's a table and it lists all the test cases. Now, it's like good news, bad news, right? Because good news is you won't have to think of the test cases yourself. They're giving them to you. The bad news is there's a whole bunch of, there's probably like 30 test cases. There's like 3 for each operation. There's like 3 for and, 3 for add, but you have to use those because if you use our test cases and you're getting the expected output, that shows that your ALU should be working the way it should be working. Now, as I mentioned in class, you also want to make sure that you're modeling that ALU is just a single MUX, right? A single case statement. Because you could have an ALU that still passes those test cases, but say you used a bunch of if statements, you could have this humongous chain of circuitry that may not work when you put it all together because it caused such a huge time delay. It might throw the timing off. Okay, but as long as you do one case statement, have a single MUX that passes all those test cases, chances are really good that it's going to be good. Okay. All right. So any questions before we start looking at the data path and control signals for these different instructions? You can see I've got 3 different branch instructions and then a couple of jump instructions. Okay, you ready to go? All right, so we're going to start with this one here. Okay, so what kind of instruction is that? Again, it would be really helpful if you had the instruction manual and you were looking at it as we're talking about this. So what is this instruction? Branch is greater than or equal. What is this here? Which one is it? Is that the destination register? Yeah, you gotta look at the instruction here. Now, you're right that when we have instructions that like add and stuff like that, that is the one. But you see, that's why you gotta look at the instruction manual. Yeah, RS1, right? RS1, this one's what? RS2. And this here, the label, of course, is a number that's an immediate. So just to put some numbers to this as we go through the data path and control signals, we're just going to assume that the program counter is outputting 80. We got an 80 right there. So that 80 was just kind of picked out of the air, but what can we always say about this output of this program counter? We can always say it's divisible by what? 4, right? Because as we talked about, each instruction in memory, right, the code segment of memory, it's separated by 4 in address, right? So this could never be like 79 or 123 or something like that. It can't be any number that's not divisible by 4. Okay, so we just randomly picked a number divisible by 4, and that's the 80. Also, just randomly picked an intermediate value. You can see here we made it a -40. And then we're going to say that the contents of register 7 is 10 and the contents of register 9 is 5. Okay, so these are just assumptions some assumptions we're making. And we're gonna see how the data flows based on those values. Okay, so again, we start at the output of the program counter where we have the address. Let's write it down. The address of the instruction be executed. Okay, then it goes to address 1 input of our memory module. So what does this read enable have to be? Has to be a 1. Once we make this a 1 and we get a clock edge, it's gonna take this address of the next instruction to be executed, and it's gonna put what at the output here? What's gonna be right here, this 32-bit thing here? That's the instruction, right? Remember again, program counter is providing the address in the instruction. At the output of the memory module, that's where the instruction is going to be, right? At the time of this edge of the clock here, provided we have an active read enable, at the time of that edge of the clock, that's when the instruction that's at this address will be here at the output of our memory module. So this output here, this is where the instruction is. Okay, then that instruction, it goes to the reg file along with the immediate generator. Now, for this instruction, which of these inputs for the reg file matter? Address 1 and address 2, right? Because we just have these source registers. We don't have a destination register, so we don't care about write address, right? I mean, there's data there again, but we don't care what it is. For this instruction, it's not relevant. So we're going to have data that we care about on address 1 and address 2. And what's the data going to be here at address 1? Going to be 7, right? That's the address of the register X7. Then what's going to be at address 2? 9. Okay, now we also have an immediate, right? The label's an immediate. So we also care about what's going into the immediate generator. Okay. All right. So since we care about address 1, address 2, we also care about these 2 outputs, right? Because that's where we're going to read the data from those addresses. So what data are we going to have at this output, RS1? So, right, we're going to have the contents of register 7, which we made 10. So the way you would write that, and some people didn't have this on their the diagrams on Tuesday, is if you just put a 7, that's a number, so that's what represents the address. If you put an X, then the number, this means the contents of the register. So having like X7 or X9 over here is incorrect. Okay, or just having 7 over here or just 9 over here is incorrect. Because this is the address, which is a number. This means the contents at that address. Okay, now we didn't put contents last time because we didn't actually put a number for the contents, but here we did. So I'm going to put the contents in parentheses. Okay, and then same thing for register 9, which has 5. Okay, now, on your diagram, and again, I put a diagram in every table, there's the ALU over here, but I didn't draw the ALU today because you're going to see these instructions, the ALU doesn't matter. The data doesn't flow. Well, data flows to the ALU, but it's not used. Okay, so that's why I didn't draw the ALU. Okay, but what does matter is this branch condition generator model. Okay, so you see RS1 data is going to go to one of the inputs of the branch condition generator, and RS2 is going to go. And this is going to do the comparison, right? This is going to see, which contents of which register is greater than or equal, which also is the same as saying which contents is less than, right? So notice the outputs of our condition generator, our branch condition generator. It's equal, less than unsigned. Okay, See, again, we only have to do 3 comparisons because these are mutually exclusive pairs. So that's why you don't see a branch greater than or equal, or a branch greater than or equal unsigned, or a branch not equal, right? It'd be redundant. Okay, so what output here matters to us for this instruction? Yeah, this one right here, right? Because we're not doing an unsigned, we're doing a sign. Now, the instruction is branch greater than or equal to, but the less than is its pair. Okay, so when you design this branch condition generator, if the output is true, it's going to be a 1. If the output is not true, it's going to be a 0. So what would the branch left hand be based on this instruction and these contents? 0. Right? Because contents of register 7, it's greater than contents of 9, but the output is less than, right? So the greater than would be 1, but the output is less than, so it's 0. So you see, this would be a 0. Everybody agree? Okay, we're not done. Okay, also what's going to happen is we have an immediate. Okay, so we got to look at this immediate generator. Well, as we said earlier, the branch instructions have a B-type immediate. And when you design this immediate generator, you use those assign statements to make all the immediate values available at once, right? Remember we said they're done in parallel. So all these outputs are going to have some immediate number. But the only one we care about is the B type. That's what matters for a branch instruction. So you see that B type immediate, it's going to go into the branch address generator. Look at what also goes into this branch address generator. There's a connection right here. And what's here again? Right, the address of the instruction, right? The output of the program. So you see, this is the module that does the offset. It's going to take the current address, right, of the instruction that's being executed, and it's going to offset it by whatever this immediate is. And it's going to do that just by adding the 2 together. So here it's going to take the 80, and it's going to take the minus 40, add them together and spit it out. Oops, I forgot to write it. Yeah. Well, we can follow that here. Let's see, where's the branch? Branch is right. So this should have branch on it. Let's JDL. Okay, so it's going to add those 2 together. And let's see, it'd be 40. Okay, so it's just adding those 2 together. Puts 40 here. And it comes to this mux. Comes to input 2 of the mux. So what does the PC source have to be in order to use that offsetted address? It's got to be 2. So then that puts that 40 right here. And then what do we want PC write to be? So it will take that address and write it for 1. Okay, so you see that's what's, it's going to be at instruction 80, right, where the branch instruction is, and the branch is going to make it branch to 40. Right, it's going to go back to the instruction that's address 40, right? So it's going to go to a previous instruction.
What is it going to do once it goes to the previous instruction? Like,
you mean once this changes? Well, then we just go again, and it depends what that instruction at address 40 is. Like, say it was a sub, then it's going to have the data path of what we did last class when we did a sub. Or if it has an and, like the one you did on your activity, it's going to have that data path for that.
so we don't choose what address it goes to, it just like picks it for us.
Well, you're choosing the address as you write the program, right? Because every time you put an instruction,
Oh,
right, yeah, and if you put a branch with a label, right, that's what's gonna make it go to, you know, some other non-sequential address. Okay,
Where does the minus 40 come from?
okay. You gotta, oh, the minus 40 here. Well, the minus 40 here is coming from the immediate generator.
Okay, so that's something we give it in ours.
Well, as long as when you, you know, when you put together the immediate generator, remember that you have the 5 types, and in order to make the immediates, you take the 25 bits coming in, right, that are 25 bits of the instruction, and then you have to, you know, piece them together. As long as that's done correctly, that's gonna be the right immediate. See, I thought you were gonna say, where does this 40 come from? Well, the 40 comes from what you're gonna design today, right? This branch address generator. And it's just gonna add, you're just gonna have an assignment statement that assigns this output to, you know, the output of the PC counter plus this B type output, and it just adds them together, and that's the output.
The -40 is the distance from, the instruction to the immediate, like the label.
Right, remember that, first of all, RARS requires labels. Okay, but even if RARS didn't require labels, from a programmer's point of view, it's advantageous to use labels instead of actually putting the number there. Because if you had to go in and edit your program and say it's a long program, well, if you know, you add or subtract instructions, you're changing the addresses of all the different instructions, right? So you'd have to go in there and manually change the immediates if you didn't use labels. But when you're looking at a data path, when you're looking at how the hardware is working, you have to treat these as numbers, because that's what's occurring in the hardware. The hardware doesn't know a label. It only knows binary, right? And that's what those numbers are. They're in binary.
How does that label turn into -40 or 60 or 120?
How does the label? Well, RARS will do that. Like when you,
Okay, so we have no, we can't tell runners what that immediate should be. We just give it a label that runners makes it some number. That's
well, it figures it out. It figures it out because, you know, if you put the label at the very first instruction, which is always at address 0, well, wherever the label is for your branch, you know, no matter where it is, RARS is going to look at, oh, you put the label up here at the first instruction. Well, that's address 0. So it'll make that label equal to address 0. Now, if RARS didn't do that, right? If there was no, you know, no software that would assign the number to the label, you would have to do that, right? Like you would say, oh, okay, I want this to branch back to my first instruction. So I got to figure out the offset, right? Oh, this is at address 20. I wanted to go back to 0. Oh, I got to make it a -20. You know, but the software is doing it for you. Okay. So any others? Questions?
You like hard code it, like could we do that? Instead of putting in a label, just put like.
Oh, yeah. Well, not in RARS. RARS, if you put a number in RARS, it will come back with an error. You have to use labels. Yeah. Now, there may be some other simulator, you know, I don't know. There might be another simulator for assembly language that allows you to put the numbers there. But again, you know, if you want to make life easy, if it allows you to use labels, that's the way to do it. But again, the reason I'm using a number here is because in order to understand what the hardware is doing, you've got to treat it like a number. Okay. Any other questions?
The branch address generator, doesn't need to have any text fail to add together.
No. Yeah. I mean, we're gonna get to it, but you know, just like this branch condition generator, code-wise in Verilog is going to be very easy to do it. Again, it's going to be 3 if-else's. This is going to be 3 assignments where you just have an output equal to 2 things you're adding.
So for the branch media generator, sorry, and then
Well, I just picked the negative value here, and you see the reason why the immediate can either be a negative or a positive is because you can either branch before, right? Like say you've got a program, say your branch instruction somewhere in the middle. You can either branch back to an earlier instruction, or you can branch ahead to a before instruction.
which one is positive?
Well, because whatever number you put here is an offset to the address you're already at, it would be positive to go ahead, it'd be negative to go back. So a -40 would take you 10 instructions back, right? Because every instruction is for an address. So this would, wherever this branch is in your program, this would take you 10 instructions back.
Maybe I missed it. Does it have -40?
Yes, yep, that's exactly what's happening. The output of the program counter that has the address of the instruction, that we're at, it takes that number and it's just gonna add it to the immediate that's coming out of the B item.
You do that, after, or? No.
Well,
it was-
when you did the ALU, right, remember the ALU, you had to add two things together, right? The two inputs to the ALU, you just took that input plus that other input. It's gonna be the same thing here. You're just gonna take these two inputs and add them together, assign it to that output.
For the ALU.
Say that again?
Oh, for the ALU?
No, it's gonna be done right here.
Oh, okay.
Yeah, no, the branch instruction and also you see the jump instruction, they don't involve the ALU.
So I thought the arithmetic, you can only do arithmetic.
Well, arithmetic on like RS1 and RS2. But yeah, this module does the offset for any jump or branch. Yeah. I mean, again, I suppose, someone could, redesign this so the ALU did this addition, but that's not how it's done in this design. Dr. Hummel and the other doctors that put this together, they decided to do it this way. They kept this separate from the ALU. It's not to say there's some other microprocessor that may use the ALU to do this. That could be.
So I'm sorry if you already went over this, but what happens exactly to the BR_L?
Well, this goes to 0 based on the comparison that's done in this module. Like you're gonna actually design this to make this happen. And,
Right.
and you see because there's only 6 real branch instructions, right? And again, the processor only has to process real instructions. Right? There's like 16 or 18 pseudo instructions that involve the branch, but the only ones that matter when you're looking at the hardware are the real instructions. Plus, they're in 3 separate pairs, right? These two go together because if one is true, the other's false, and vice versa, right? So inside this branch condition generator that you're going to design, you only need 3 if else. And these 3 were the ones that were chosen for the outputs. Again, if it was some other design, someone else might have made this, branch greater than or equal, branch greater than or equal on sign and branch not equal, right? And those values would just be flipped if that was the case.
But like, what happens to the back, like, the 0 when it goes to the C?
Okay, well, that's for later, okay, yeah, because, the control unit, and if you look at the output of the control unit, what do you see when you look at the output of the control unit decoder? Exactly. So you see, when that goes into the control unit, that's gonna tell it, hey, I need a 2 here for this mux. Okay. Yeah, and also, you'll also have something in your FSM too to make sure that the writes and the reads are the right value. But yeah, that's something that we'll get to later. That's in a couple of weeks. Was there another question over here? Did you have same question? Okay. All right, yeah, great questions. Okay, any other questions before we move on? Okay, the next thing is, what if the contents of these two registers, what if they were swapped? What would the only difference be in what we've done here? What was that? Yeah, the only difference is this output would be a 1 now instead of a 0, right? Because we have the other case. But everything else is the same. The data, the control signals, everything else is the same. The only difference would be the comparison in here would be the opposite result. Okay? Okay, so let's see. We did this one. Talked about this. All right, let's do this one here. Now, this is where I'm going to do a shortcut as long as it's okay with everybody. Now, what instruction do we have here? A BLT is what? Besides a delicious sandwich, it's what? That's a branch shift left hand, right? And that's the other, the other one of this pair. So because it's just the other one of that pair, we can take a little bit of a shortcut here. But before we do, what's this here in the instruction? Like RS1, RS2. Thank you. Now we're going to assume that we start at the same program counter output, this address of 80. We're going to use a value of 60 for the immediate. We're going to say that in register 12 is contents 12, in register 10 we have contents 12, in register 12 we have contents 14. Well, instead of erasing everything, okay, like I was doing in class 4, I'm going to take a shortcut. I'm going to leave the red and blue up here because the data path's going to be the same. Now the addresses are going to change and the contents are going to change, and we may have a different result. Okay, but I'm not going to erase everything if that's okay with everybody. I'm just going to kind of modify what's up here. Is that okay with everybody? It'll save a little time. Yes. Okay. All right. So again, we would start here. We're keeping this at 80. We want that to be a 1, right? This is going to be the instruction again, right? Okay, what's going to be different here? We don't have the same addresses, right? So what are we going to have for address 1? What do we have? What is it? 10. Okay. And then what are we going to have for address 2? 12. So this is going to be 10. This is going to be 12. Okay, what's the contents? 10 is 12, right? Or yeah, 10 is 12 and 12 is 14. Okay, so that's going to come up here to the branch condition generator. And what output would we get? 1, because content, right? It's comparing this against this. If this is less than that, true. So yeah, so this would change to a 1. All right, this would no longer be minus 40. This would be 60, right? And then what would it output? 140, because it just add those two together. Do we still want this to be a 2? Yeah, still want that to be a 1. This would just change to a 140. So it would go from address 80 to 140. So that's an example of it branching ahead in the program. Right? It would go what? 60 divided by 4. So it'd go like 15 instructions ahead. Okay. So does that all make sense? Again, if you miss writing any of this down, it's on Canvas. The solutions are on Canvas. Okay, now how about, let's see, we did this one. Okay, how about this question here? Okay, so we have these two pairs and these two pairs. One's treating the data as signed, the other one's treating the data as unsigned. So where would the differences be between, these two where the data is being treated as signed and these two where the data is being treated as unsigned?
RS1, RS2 still.
No, this is gonna be the same data. Yeah, just here. It's just how you treat it here. Like one of your if else's will treat what's coming into it as signed, and another if else will treat it as unsigned. Okay, so the difference is in here with the comparison, and then also, of course, you have this output instead of that output. Right, because we have a separate output for the unsigned comparison. Okay. All right, let's see, one more branch before we get to the jumps. So let's look at this one here. Again, I'm not gonna erase everything because you're gonna see the data paths are the same. But what kind of instruction is this? Oh, you have a question?
Yeah, so when we have one, the outputs high, BCG, and the other is zero, right? The other is low.
Correct.
In the last example, it was in the low, right? So would that mean all three are low?
Oh, that's a good question. I guess it depends on how we design this decoder. For the purposes of this assignment, you only have, for each comparison, you only have to worry about its corresponding outputs. So like when you're doing the comparison for, the branch less than or branch greater than or equal to, you're just gonna put what that output would equal based on the comparison. Okay, but you're right, your question brings up that when you design this, you've got to make sure, and you can do it by like initializing outputs to zero and things like that, but yeah, you got to make sure that you're not inputting like two truths or conflicting information. So that is something to be concerned about, but not today. Because we're gonna deal with this later, and then we'll come back to it.
Okay, but for this assignment, those are all operating something. Then making your own comparisons for the two inputs.
Well, it's just gonna be, each comparison has its own if else. So you'll have an if else for, whether it's equal or not, an if else whether it's signed less than or it's less than unsigned. So it's just 3 if else's, and you just have to put that particular output in the if else. But like I said, in the future, you might have to come back to that, and depending on what you do in this decoder, you may have to modify it. But for today, don't worry about it.
Is there a reason why RS1 and RS2 are affected with the DH module?
Yes, we haven't gotten to that yet, but there is a reason. It's because of one of the jump instructions. Yeah, just like also there's a reason why there's a connection here today, but it involves the jump. But we'll get to it. Okay, any other questions before we look at this branch? Okay, so what does this branch instruction do? Which one's this? Branch not equal to, right? Okay, so what do we have here? What is this? RS1, RS2, and then we have our immediate. Okay, again, we're just going to assume the programmer's at address 80. This label is equivalent to a 120 immediate, and then here's our content. So again, I'm not going to erase the data path because it would all be the same. We're just going to modify what we have here. So this is still 80. This is all the same. This is going to be a different address, right? What's the address of, or what do we have on that input? Address 1? 20? 24? Okay, and then this would be contents of 20, which is what? 1. The contents of 24, which is 2. So what would the output of the branch condition generator be? Right, this branch equal would be 0, because they're not equal. If they were not equal, it'd be a 1. Well, if this was a branch not equal output, it'd be a 1, but because it's a branch equal and they're not equal, it's a 0. All right, and then also here we would still have 80 coming into the branch address generator, but this would now be 120. So it, yeah, 120. So it adds those two together, 200. Yeah, thank you. Right, so that 200 is coming in here now. Do we still want this to be a 2? We want it to be a 2. Right, and then that would put the 200 here. And then to actually write it to the output of the PC, right, we'd want that to be a 1. So it would jump from address 80 to address 200. So that's what? That's 120. So that's like 30 instructions ahead. Right, because you take 120 divided by 4, that gives you the number of instructions. Okay, so any questions on that one? Okay, so we have an option here. Do you want to take a short break for 5 minutes, or do you want to keep on going? Keep going? Okay, we'll keep going. All right, so those were the branch instructions. Now we're going to look at the jump instructions. And there's 2 we're going to look at that are the real instructions. There's this JAL and JALR. So first, let's look at this JAL. So what kind of instruction is this? What does the instruction manual tell us? Does it say just jump? No, I got it. Yeah, it's, well, specifically an unconditional branch, which is a jump, with an offset and a link. Okay, the offset is no different than what we were talking about with the branch. That's the number, the immediate that, you know, offsets the present instruction address. But link we haven't talked about. Okay, but what I've written up here, this is what the link is doing. That's what this L stands for, is link. Okay, it's going to take the address of the next instruction, right? So it's going to take the address of the instruction that's after this instruction in the program, and it's going to save it to whatever register that we specify here. And the reason you may want to do this is because after whatever you have jumped to is finished, you may want to go back to the instruction that's after that jump. So that's the reason for saving the address of the instruction that's after this jump instruction. Okay. Now, this is something that you have to be aware of, because this is something that can really, you know, provide a problem. Because we're saving that address, that PC+4, it's possible that you could overwrite data that you don't want to overwrite, right? Because if it takes that address, and you'll see it's going to save it in the reg file, just where, you know, we save all our data. Well, if there's something in that register that you're saving that address to that you need for something, you know, something else, well, it's lost, right? Because once it writes that address to that register, you've lost the previous data. So this is just something you have to be concerned about. And what you can do to play it safe and make sure that you don't overwrite data, you know, that perhaps you need, is that you could just specify that this register where the address is going to be saved is register 0, right? X0. And what's special about register 0, X0? It's always 0. So you see, if you try to save something to register 0, it's just going to make it 0. Okay. So that's what the jump instruction does. If you just have a jump instruction, it's just taking that PC+4 address and it's basically just getting rid of it. Okay, because you know you're not going to use it and you don't want to overwrite anything that you could possibly lose. Okay, so that's what the L here, the link is talking about. It's taking the next address in the program after that jump instruction and saving it to a register. If you don't want to do that, you got two options. You can make this X0 in this instruction, or you can just use a jump instruction.
But like, what specifically does that instruction do then? In the context of our survey?
Well, we're gonna go over the data
Oh, okay.
path, and we're gonna do that right now. Yeah, but I just wanted to explain what this L means before we did that, because now you're gonna see how it actually does it, like the data path. Okay, but that's sort of like the reason for this instruction. Okay, so here I am going to erase what we had, because you're gonna see it's different. Quite different than the other three. All right, let's go to this. Start from the very beginning. All right, let's. I think I got rid of everything red and blue. Pretty sure. All right, so this is the JAL instruction. So we're going to assume that the program counter is at 120 to start with. And then also well, actually, I should ask you. So in the instruction, what is this X16? The RS1, RS2, RD? It's RD. And again, this is our immediate. And you can see we're just going to use an immediate of -100. All right, so just like any instruction, it starts at the output of the program counter where the address of that instruction is at. Okay, we go to this address input of the memory module. What do we want this read enable to be? A 1. Okay, so now that instruction's at the output of our memory module here at POut1. Okay, so what matters here as far as the reg file goes? Do we care about address 1? No, there's no RS1. Do we care about address 2? No, no RS2. Do we care about write address? Yeah, because there's a destination register. Okay, what data is going to be on there? 16. The address of that register is 16. Does the immediate generator matter here? Yes, it does. And what kind of immediate does this instruction have? And how would you find out if you didn't know? I mean, I wrote it on the board, but where do you go look to see that it's J-type? Right on the description of the instruction, right? Where the machine code is, they'll see J-type. Okay, so it's the J-type output that matters. Okay. And then also, it's going to take the program count. It's going to add those two together. And it's going to output on this output here. All right, so it's just going to add those. I forget the right. What is it? -100, -100. Here. So it would take 120 and -100, add them together. It's going to put a 20 there. Okay, so what would we want on PC source here? What? Three. That's gonna connect the JAL input to the output. Right, so that's gonna put the difference of 20 here. Now, we would also want this to be a PC to write a 1, so we go to that next address, but there's something else that has to occur here, and that's the link part. Right, because again, this link part is we want to save the address of the next instruction. So where is that address? Where is PC plus 4? On the hardware. Where is it? Right here, isn't it? Okay. Oops, wrong color. All right, remember in your program counter, you have that part where you're incrementing the current instruction address by 4, right? Get ready for the next instruction. Well, you see, that's why you have this connection. Okay, there's this connection going to the MUX, whose output goes to write data, right? Because that's where we take the data and write it into a reg file register, right? It's this data here. Right? So, oh, I forgot to write the select line for this MUX. That's something I forgot. I think this is what RF. What do they call this? RF underscore what? WR select. That makes sense, right? Register file write select. Sorry about that. I forgot to put that on. Okay, so what do we want this select line to be? 0, because it changes that input. Yeah. So that will put the data. That will put the PC plus 4 right at that right data input, and then to actually write it into the specified register, register 16, I need the reg write enable to be what? 1.
Isn't it just the address? No? Or no, it comes from the EDG.
Are you talking about this? Yeah. Remember, here's the address that's being executed. Here would be the next address in the program. And that's what we're saving, right? We're saving the address of the instruction that's right after this JAL. Yeah. And again, the reason for that is you may want to, you know, after you're done with whatever the jump is doing, you may want to come back to that. So we see here, whatever was in register 16 before this instruction, it's not going to be there after, right? Because it's going to get written over. Now, if you don't care about that, that's fine, right? But you just got to be aware, because, you know, if later in the program you go to get something for that register and you think it's something else than that return address, then, you know.
So what's the value of the, what's the value coming out of the PC input plus 4?
Oh, right here?
Yeah,
This, in this example, it would be 120.
okay.
So this would be 124. Yep. Yeah. Okay, so any more instructions on this one? We got one more instruction to go. All right. You okay? All right, so let me erase these lines again. All right. I think I got all the red input. No, I got the input. It's Yeah, I think I got it. Oh, no. Okay, so I think we're ready for the next. All right, so this one here, this is a JALR. And as you can see, the difference is that R. And what do you think R stands for? What? I couldn't hear you, sorry. Register?
Yeah.
Return, oh, no, not return. It actually has to do with the register, because you'll see that this instruction involves a register. Well, actually, you can see it right here, right? It's X31. So what is X31? Any guesses? Well, this instruction has L in it. This instruction has L in it, just like this one does. And what does L mean? Linked, which means you're saving an address, right? The PC+4. So it means the same thing here. So this is also a destination register. All right, but now look at what we have here. This is different, a little different than what we've seen before. When you saw something like this in a load instruction, where this is acting like an offset to what's in the parentheses, it's the same sort of thing here, but what's different is this doesn't represent an address, because in the load instructions or the store instructions that have that offset with some value in parentheses, that whole thing's acting as an address. But here, this whole thing acts as an immediate. So it's just that in this instruction, we're getting the immediate by taking this number out front and adding it to the contents of this register. So these two things are added together, and then that becomes your immediate. And that's what's going to provide the offset, to make the jump happen.
On table 12 for the instruction overview, it has like 3 different ones. Why is that? They have one where it has RD, RS1 immediate, has a separate one just for RS.
Right. Yeah, I guess there's different ways that you can write the second part of it. Now I'm not sure why they have the RS1 in. I'm not sure about, yeah, because also in the detailed description, it has like 4 options.
Yeah.
And 2 of them that have RS1 instead of RD. I'm not sure why that is so. I'll have to look into that. Because, again, because of the L, this makes sense, right? Because link means that you want to save something. In order to save something, you need a destination register. So I'm not sure why in the other 2 options is an RS1. I'll have to look into that. But whatever it is, it's something I haven't run into before, so I don't think it's anything you're going to run into. But I will look into it, because I'm curious now too. Yeah, I don't know why. It doesn't seem to make sense that you would have a source register for this command. Yeah. Although this is a source register here, though. That's true. X13. Oh yeah, so this would be RS1 here. But still, the other 2 commands that you're referring to, oh, they both have a, oh no, they only have an RS1 for those 2. So yeah, I don't see how you can do a link without an RD. So for right now, I would ignore those 2, because it could be that maybe they're typos. But I'll check into it. Okay, yeah, so this register that you put in the parentheses, that's source 1 register. All right, so let's go ahead and let's do the data path now. So again, we start here with the address of the instruction. We want this enabled to be what? 1. that's gonna put the instruction in here at the output of the memory module. Now, do we care about address one? Yes, because this is RS1 here. So we care about address one. Do we care about address two? No, because there's no RS2. Do we care about a write address? Yeah, because there is a destination register. Do we care about an immediate? Yeah, because this, like I said earlier, these two together, that's our immediate. So we do care about immediate. Okay, so what's gonna be, well, actually, let's put the numbers here. What number do we have here for this address one? What's gonna go here? 13. How about the address for our 31? So what are we gonna have at the output of RS1? Right, the contents of whatever register 13 has. We didn't put an actual number. Well, this is just a number that's getting added to whatever contents of the register are, and then together that's the immediate. Oh. So by itself, this is just, like the output of RS1 is just whatever is in that that register 13. Okay. Like we could give it a number. All right, you can see that goes down to our branch address generator. Okay, and then what type immediate for this command? It's an I type. So the I output of our immediate generator is the one that matters. So you see what this branch address generator is going to do. It's going to take these two inputs. It's going to take the contents of register RS1 and add it to whatever this immediate is. And that's what's going to be at the output of JALR. This would just be, let's see, what was the 80? See, this would be where the 80 is. So out at this output would be 80 plus the contents of register 13. Okay, and then that comes up over here. So what would we want PC source to be in order to use this? A 1. And what would we want PC write to? A 1. Okay, but we also have, just like with the JAL command, with this command, we also want to save the address of the next instruction after that JALR. So that's why, again, you see this connection from the output of a PC +4. Goes over to this mux. So we want this select to be a what? 0. Okay, that puts that data here. And then, well, I didn't erase it before, but this would still want that a 1, right? To actually write the data into this register that we're going to save that PC +4 address. Okay, so the difference really between the JAL and the JALR is with the JALR, you're using the contents of a register along with some number to give you the new address that you're going to jump to. Okay, so any questions? All right, let me just quickly go through what you need to do in Verilog, and then let me just talk about what's left the rest of the quarter and also what's due, and then you can go ahead and start working on whatever you need to work on. There's no activity today. All right, so I've already mentioned this in the course of the lecture, but just to emphasize, the code for these two modules, the branch condition generator and the branch address generator, is very little. For this branch condition generator, it's just 3 if-elses. You just need an if-else for each of these 3 comparisons. Okay, so it's going to be a very short amount of code that you have to write for this. And then the branch address generator, same thing. Not much code at all because the branch address generator, it's gonna generate these outputs, right? The offset to your current instruction address. It's gonna do that in parallel, just like the immediate generator was generating the immediates in parallel. So when you modeled the immediate generator, how did you do that since outputs are all in parallel? Yeah, you just did assign statements, right? Same thing here. These three outputs, they're just, each output's an assign statement. And, you know, for branch, you're taking the PC, adding it to the B type. For JAL, you're taking the PC and adding it to the J type. For JALR, you're taking these two inputs. You're taking the I type along with the contents of register RS1 and adding them two together. Okay, so your branch address generator, it's just three assign statements and you're just doing addition. You're assigning output to two things you're adding. Okay, so it's not much code at all for either one of these modules. Okay, so last thing here before you get started, because we're halfway through the quarter now, I just wanted to kind of outline, just kind of remind you, you know, what's left. Again, this is all on Canvas, but I thought I'd just take a few moments here in class in case you had any questions. So this is sort of the schedule that's left. Remember, next class on Tuesday, we have the midterm. It's the first hour of class. You know, most people have been really good about being here on time. There's been a couple people that, you know, not so good. I see a couple of empty seats over there. You don't want to be late on Tuesday, okay, for the midterm. If you're late, you're going to lose that time. If you come in 30 minutes late, then you only have 30 minutes in the midterm. Okay? If you miss it, it's a 0. So you got to be here. So make sure that you're here on time on that day. So first hour is the midterm. The last 2 hours, although I don't think it's going to be a very long lecture, will be on arrays. Okay, how to do arrays in assembly. And here you'll see how you can put data into the data segment of the memory module. You know, we haven't really talked about the data segment of the memory module or the stack yet, but we will talk about that data segment when we talk about arrays. Okay. And then Thursday of next week and the following Tuesday, which is after the 3-day weekend, the 20th is President's Day. Both those lectures are on the control unit. Okay, the control unit's going to take some time to talk about. Okay, you know, that's where you spend most of your time in the last 2 assignments for hardware. And then the 23rd of the week, we have the 3-day weekend. That's when we talk about the auto wrapper. That's the circuitry that goes around the CPU that allows you to interface it to switches and LEDs and 7-segment displays that are on your basic board. And then the last in-person class we have is on the 28th of this month. And that's when I'll talk about how you do, well, what the stack is and how you do subroutines in assembly. Okay, and then on March 2nd, which is Thursday of the 8th week, that's an open lab. Okay, so that's a lab where if you're behind on something, you can use it to catch up, or if you're all caught up and you want to try to get ahead on the final projects, it's a lab where, you know, you can come here or not come here, it's up to you, but it's an open lab. And then the last 2 weeks are devoted to the final projects. There's a software final project and there's a hardware final project. And I'll talk about it in more detail as we get closer, but you know, as I talked about on the first day of class, the first was it 15 meetings or so are in person, and then the last 5 meetings, you're not required to come to class. You know, I'll be available on Zoom during that time, but the lab is still open. So I mean, if you want to come in here, you're more than welcome to, but there's not any set class time the last 2 weeks. Because it's time for you to work on the final project. It's not time for you to take a vacation. Okay, it's still work for you. That's you can do it whatever you want. Okay, then there'll likely be 2 more in-class activities, and they'll probably be for hardware number 6. And I'll talk more about hardware number 6. But remember, the in-class activities, you do have to be in class to get credit. Okay, there's no makeup for the activities. Now, if someone's absent because of a university recognized reason that's documented, I just won't count it. But in order to get a score for an in-class activity, you do have to attend class. That's why it's called in-class. Not called at-home activity. Okay, and then due dates. All right, I wanted to point this out because remember, last class I said, okay, well, because we have the midterm Tuesday of next week, I'm not gonna have your ALU and immediate generator due before the midterm. Same thing with the branch address generator and the branch condition generator. I made them due after the midterm. But the thing I wanted to point out, because even though these are due after the midterm, I wouldn't wait till after the midterm to begin with. Okay? Because hardware number 4, which is the ALU and immediate generator, that's due the day after the midterm. Okay, that's due Wednesday the 15th. The branch address generator and branch condition generator, they're due Friday of next week. And then arrays, which again, we're going to talk about after the midterm, that's going to be due the 21st because Monday the 20th is a holiday. But this is what I wanted to point out. You're going to have 3 assignments due within a week's time after the midterm. Okay, so that's why I don't, just put everything off and try to do it all after the midterm. You should still be working on it. It's just if you get in a time crunch, coming up on the midterm, well, the midterm's the priority, and then just come back to this afterwards. Okay, and then after that, things are due like on a weekly basis. Hardware number 6 isn't due until like March 3rd. So you see, you have like a couple of weeks between this assignment and the next one. And the reason for that is hardware number 6, that's when you're designing the control unit. So you won't be able to start hardware 6 until after this second part of the control unit lecture. And that's when you got to have your diagrams for all your instructions ready. Okay, so there's a fair amount of work for hardware number 6. Okay, and then the following week is when the software final project is due. And then the last week of the quarter is when your final hardware project is due. And that's when the otter should all be working and you can program it to do something. And I'll talk more about the final projects and probably next week. Okay, and then there is an online final during finals week at the university time, and it's just going to be a true false type of test online. And again, I'll talk more about it when we get closer. But what I wanted to do at this point was just to give you an overview of the schedule and also what's going to be due for the rest of the quarter so you can kind of prioritize things. And again, this is all on Canvas too. I'm not changing anything that's not already on Canvas. I saw Cadence in and then I'll come back here again.
So we have our final.
Yeah, well, I have to do that because university sets days and times and I can't go outside. So it's not gonna be a 3-hour test. I think it'll probably be less than an hour. Just something it's near involved about.
Will it be graded the same as our midterm? It's like if you don't answer it.
Right, yeah, I'm gonna discourage it. Oh, question.
Was there any particular reason why we lose a point and a half if we get?
Yeah, well, no, what it is that if someone just, okay, this is my thought process. If somebody reads a question and has, absolutely no idea, like you just don't know at all. And the person just, randomly chooses something and gets it right. Well, that's not really, from my point of view anyway, fair to a person who really knew it. So that's why I'm discouraging guessing, right? So if there's a question that, again, you absolutely have no idea, you shouldn't answer it because if you do and you're wrong, it's going to be more taken off than if you have an incorrect answer. But if there's a question, well, hopefully most of the questions you're going to be like, oh yeah, Perks is great. This is easy. Hopefully. No guarantees. I don't know. I'm hoping for that, right? So hopefully most of them like that. But then there's bound to be some where you look at and you say, oh, it might be this. I know it's not that one. It might be this one. So then you got to make a choice, right? And again, it depends on your risk tolerance, right? Are you a person that invests in CDs or are you a person that, is a crypto person, right? I mean, yeah. But yeah, by discouraging guessing, in my point of view, you might have a different point of view, but in my point of view, I'm benefiting the people that really know. I think that's how I look at it. Now, again, you may disagree, but. Any other questions? All right, well, you have the rest of the time to work on whatever you need to work on.